We will start chapter 4 by learning about electrolytes, which are compounds that conduct electricity when they're dissolved in water. So which means really we'll be talking about all the sorts of compounds that dissolve in water and reactions that occur in water. And considering the fact that the earth is made up of 70% water, it's a very important class of reactions. The first class of reaction we'll deal with here is precipitation reactions, the reactions that give you a precipitate or a solid as a product. Okay, so these are the topics that we will talk about in this little PowerPoint. So let's talk about solutions. Okay, and solutions are made up of two things. Okay, a solute and a solvent. A solute is the component that is dissolved, and the solvent is what does the dissolving. Okay, solute is the smaller quantity and the solvent is the larger quantity in most cases. A solution can be of any kind, okay, which means it can be a solid in a liquid, liquid in a gas, whatever it is, but it should be a homogeneous mixture, okay? That's the key thing. Otherwise, it will just be a mixture, in which case it could be a heterogeneous mixture also. In any case, aqueous solutions are in which the water is the solvent, okay, which is the larger quantity. The water is the solvent, and the solute then can be anything, liquid or solid or gas, okay, for that matter. But the solvent is water. There are two kinds of things that happens in solutions for anything that you dissolve in it to the solute. So the solute can dissociate in the solution, or it can ionize in a solution. In case of dissociation, this is primarily for ionic compounds. And in case of ionic compounds, the compound will dissociate to give the cation and the anion. Now remember, ionic compounds are made up of metals and non-metals. And so they are held together pretty much with a force. Okay, there is no particular bond in here. So when they get into the water, they actually dissociate, okay, into giving cations and anions. Remember, we've talked about these S's and the AQ before, and the S is for solid. And AQ is for aqueous, okay, which means it is dissolved in water. Ionization is by molecular compounds, and molecular compounds are the covalent compounds, which is on the right hand side of the periodic table. So for example, we can take hydrogen chloride, which is a gas, and when it is dissolved in water, it ends up giving hydrogen ions and chloride ions, which is really quite unique for HCl, because hydrogen chloride should not be able to dissociate, but it does. Okay, and we will talk more about how this happens in the later chapters. Okay, for now, you just have to memorize this. One other example is that of ammonia, which dissolves in water to give ammonium ions and hydroxide ions. This arrow, I should tell you, I should introduce this to you. This is an equilibrium arrow, which means the reaction can go forward as well as in reverse. Okay, we will probably not see this too much in this semester, but because it's there, I just want to tell you what this is. In this case, in this reaction with ammonia and water, we have different phases also. So ammonia is a gas, water is a liquid. Remember, water is never going to be AQ, because AQ stands for aqueous, which means something that is dissolved in water, not water itself. Water by itself is liquid. And so then you get ammonium ions and hydroxide, which are both AQ, that means dissolved in water. So these are the two different things that happen. As far as I am concerned, dissociation is going to be our key thing. Some ionization too, okay? But I will refer most times to formation of ion. Let me go over a little bit more about how to write dissociation equations, because this is something you will have to do for all the equations you will learn in this chapter. So first of all, ionic compounds are the one that gives you ions. We'll talk about covalent compounds also, but one thing at a time. So ionic compounds, for example, calcium chloride. So the first thing you have to know, of course, is the formula for calcium chloride, which is CaCl2. Do not take the wrong formula. So know your nomenclature well. When you dissociate something like calcium chloride, you will get calcium and you will get chloride ions. There are a few things over here that you need to know. First of all, what is going to dissociate? If something is ionic, it will dissociate. Second thing, what is it going to dissociate into? So calcium and chloride.
which means those are the ions you get. The second thing is how many ions will you get? So in the formula you have 1 mole of calcium, so you will get only 1 mole of calcium ions, and then you have 2 moles of chloride ions, so you'll get 2 moles of chloride ions. The Cl2 here shows you that there are 2 chloride ions, so which means this 2 actually goes here as a coefficient. So that shows you that the mole ratio in calcium chloride is 1:2 of calcium to chloride. Okay, so the wrong way of doing it is the Cl2 minus. This is a very common mistake, so try to avoid it if you can, or well, you must avoid it. So do not leave it as Cl2 as a subscript, but you need to bring that 2 as a coefficient. Okay, so that's the important thing. That way you keep the compound as in balance, and then you know how many moles you have. So then you have to make sure that you write the proper valencies. So for example, calcium is supposed to be +2 because it's in group 2. So make sure that you write this as calcium 2+, and chloride is supposed to be -1. So you write the -1. Now, technically speaking, if you add up all the charges on the right hand side, they should add up to 0. So this is 2+, and this is 2 minus, so they should add up to 0. It should be neutral on the left and the right hand side. Okay, so if you have more of the minus or plus on one side, then of course there's an imbalance, and then you have to put a coefficient somewhere. Generally, if you do everything correctly, you should not have an imbalance. Let's take another example here of magnesium phosphate. So this is the formula for magnesium phosphate. Now, when you dissociate something like this, which is a polyatomic ion, then do not dissociate the polyatomic ion, which means do not separate the phosphorus and oxygen. Whatever is in parentheses or not, for example, sulfate, SO4, may have been only one in combination with magnesium, but you still don't separate it out. So leave the polyatomic ion as it is unless you're told to separate it. Okay, unless the equation calls for it, don't do it yourself. So here the magnesium phosphate is going to dissociate to give you 3 of the magnesium ions and 2 of the phosphate ion. So make sure you keep the phosphate ion together. As in PO4, the charge on the phosphate ion is 3-, the charge on magnesium is 2+, and the subscripts down here become the coefficients up here. Okay, that's how you would open up any kind of a formula when you're writing dissociation equations. And again, this is an important part because you got to do all of these equations as we go through this chapter. And then finally for the covalent compounds. Now for most of the covalent compounds, you will not have any dissociation for them because they are not ions. They are covalent compounds. The only things that will dissociate are going to be acids. Okay, and acids, for example, H2SO4 is going to dissociate as hydrogen ions and sulfate ion. So here sulfate is just 1, as I was saying before. So SO4 is right here, but then of course you have to give the ions because these are ionic equations. So this is 2-, and then you have 2 of the hydrogens, so you'll put 2 as the coefficient and then H+. Again, remember, do not leave it as H2. You have to write it as 2H+. Okay, that is how you will write these equations. It takes a little practice, so please make sure you do practice, okay, on writing dissociation equations.
So when you have dissociation going on, we actually end up forming something which is called an electrolyte. And so electrolytes form a solution that actually conduct electricity, okay? And an electrolyte will contain ions because, as you saw in the previous slide, is when you have any kind of dissociation going on and you produce ions, those ions then will have their own property, and one of that property is that they start conducting electricity. Electricity is conducted primarily by negative ions. Okay, you need electrons for it, and so if there are any anions in there, which of course if there is cations, there is anions. If there's anions, there's cations. You have to have both in a solution. So electrolytes will conduct electricity. Okay, that is the mark of a solution, okay, of an electrolyte. There are 3 kinds of electrolytes: a strong, a weak, and a non-electrolyte. A strong electrolyte is one in which the substance has dissolved completely, okay, which means there is 100% dissociation. There is nothing left in the solid state or gas state or anything like that. Okay, so it's 100% dissociation, and this is typical for a lot of ionic compounds, strong acids, and strong bases. And I will give you examples of all of these, okay, in a few minutes. Weak electrolytes are when substances are partially dissolved, okay, in water or partially dissociated in water, which means that you still have some of that starting material left in there, okay, which is true more for molecular compounds, which is the covalent compounds, okay. So they sometimes don't dissociate all the way through, which is why you see that equilibrium arrow, okay, because then you have the forward reaction going on as well as the reverse, right? That's where you have molecules forming as well. So the weak acids and the weak bases, they actually form weak electrolytes. And then finally, we have non-electrolytes. And in case of non-electrolytes, these are solutions that do not conduct electricity at all, which means that a substance has dissolved in the water, but it does not contain any ions, okay, whatsoever. So if it doesn't have any ions, it's not going to conduct any electricity. And those are called non-electrolytes then. So how do you know that you actually have electrolytes? Well, you go ahead and put a bulb, okay, and connect the circuit, okay, to the solutions, and then you find out, okay, if you have a strong, weak, or a non-electrolyte. So for example, if you have a non-electrolyte that is not ionized in there, the bulb will not light up. If you have a weak electrolyte, then you have a few ions in there, not too many. And if you have a strong electrolyte, then you have many ions in there, and then the bulb lights up completely, okay? And so it's quite easy to figure out using a light bulb whether you have a strong electrolyte or not. Here are your examples of strong acids. The most common acids that you will encounter are going to be hydrochloric acid, nitric acid, sulfuric acid. Okay, these three are the most common ones. The other ones are also strong, but you don't encounter them so much in general. Okay, and don't worry about this equation at the bottom. You will talk about this one more in Gen Chem 2, not so much right now, okay? But hydrochloric acid, nitric acid, sulfuric acid, remember these are strong acids, which means they dissociate completely. One thing we should talk about for electrolytes is the practical applications, okay? And you hear about electrolytes all the time. You should maintain your electrolytes, drink your electrolytes. And if you go to the grocery store, you will see that there is an aisle that just is dedicated to electrolytes, okay? And so let's talk about electrolytes. We have electrolytes in our body because our body is made up of 70% water. So we have ions in there like sodium, calcium, potassium, chloride, carbonate, sulfates, and some other ions that we have. And all of these ions are there for a reason, okay? And so some of those reasons are to maintain the voltages, to carry the nerve impulses, and with the muscle contraction. So if we don't have these ions, then we will have a problem in all of these functions. Typically, we get our electrolytes through our diet. So you drink them or you eat them. Okay, pretty much that's how we get our electrolytes. And really, if you're eating a balanced diet, you should not have any issues of having enough electrolytes in your body. The kidneys in our body are responsible for maintaining the electrolytic balance. Okay, and so all the liquid that has to excrete from our body goes through the kidneys, and they take care of this. If the ions are not in the correct concentration in our body, then of course any of these problems can happen, and then they have to be treated medically. One of the easiest ways that we lose electrolytes, and this is a common thing that happens, okay, is during sweating. So typically we won't lose electrolytes any other way, but mostly, or if the kidney is malfunctioning, then you will lose electrolytes, or you will lose electrolytes during sweating. And so hopefully everybody's kidneys are fine, so which means that if you sweat, then you lose electrolytes. And we lose them in two ways, okay? One is that you lose water, and because you lose the water, the concentration of ions changes in the body, and that can also change these functions. And the other part of it is that we also lose ions during the sweating. So it's not just water that you lose, it's also some of the ions. And so when we talk about hydrating our body, hydrating is trying to create that balance back. So if you're not sweating too much, if it's a light sweat, then you can just go ahead and hydrate yourself, which means just drink some water and you can restore the balance. But if you're sweating a lot, so for example, if you're a player or you're an athlete and you're outside and sweating, then you need to replenish, okay, those ions, or you might actually lose some muscle control. And that is why we have what are called the electrolytes. Okay, these are the sports drinks that you find, and these will have all the commonly used ions, okay, in them, and so they replace those ions in the body. The only problem with these sports drinks is just to make these electrolytes a little more palatable. They are very sugary, okay, very, very sweet. These electrolytes are not all that tasty, okay, in general. So it's not like you can just have a spoonful of electrolytes. And so if you're drinking these, you're hydrating your body. You To make it tasty, you have to add sugar to it. Okay, so that's the only problem with the electrolytes. Otherwise, those are really good for replenishing all the ions in your body. The first electrolyte beverage was invented in Florida. And can you guess the name of it? Yes, Gatorade. Okay, and so Gatorade was the first electrolyte that was invented, and it was because all the players were outside all the time, and so through some research, they actually figured out that they were losing electrolytes and then created this electrolyte beverage. So look at the colors also, orange and green, very Florida, very Gators. So now for the different kinds of reactions that can actually take place, okay, in water. We've talked about different classifications before, and I'm going to introduce one more, okay, to you. So there are two different kinds of classifications. The first one that you have done is the atomic rearrangement, which was the synthesis, in which case you combine two things and get one thing. A double displacement, in which there is two exchanges going on. That is called double displacement. Then we talked about a single displacement, in which case one element would displace the other one, okay, and so you would still have the same number of chemicals on either side. And then decomposition, in which you start with one compound and you end up with two products in the end. That's decomposition. It's the opposite of synthesis. This is what you did in the previous chapter. In this chapter, we'll talk about the chemical reactions that are taking place, not in an atomic form, but in a chemical way. And the chemical reactions are classified into three: precipitation reactions, okay, where a solid is formed; neutralization reaction, when an acid and a base will react to form salt and water; and then oxidation reduction reactions, in which case we talk about either the addition or removal of oxygen or transfer of electrons. Okay, so this is a chemical classification, and this is what we will focus on for this chapter, okay, for the first part of this chapter. So the first type that we will talk about is the precipitation reaction. The precipitation reaction is when you have two solutions combining, or you're adding two solutions and you form a precipitate, okay, which means that the product that is formed from that reaction is insoluble in water. Remember, aqueous solutions are homogeneous solutions, okay, which means you can't really tell if something is in there, all right? So if you take two homogeneous solutions and you add them together, you may end up forming a compound that is not soluble in water, okay? These are usually ionic reactions, and if you remember a few slides ago, I mentioned to you that a number of ionic substances are soluble in water because they form electrolytes, okay? Well, now you have a little bit more information. And the truth is that not everything is soluble in water. If everything was soluble in water, then we would have no earth, we would have no rocks or mineral or sand. So not everything is soluble in water. Okay, and so those are precipitation reactions, which means that those kind of ionic compounds then will not be good electrolytes, okay, or strong electrolytes. There may be weak electrolytes, but not strong ones. The reaction type for this kind of a reaction is double displacement, which means two exchanges going on. How do you define solubility? It is defined as the maximum amount of a solid that can dissolve in a given amount of solvent, okay, at a given temperature. You will learn more about this in Gen Chem 2. Okay, we will not cover too much of this now. However, you do have to know how to predict whether a precipitate is going to form or not, and this is based on solubility rules, okay, and this is something that you just have to memorize. There is no other way for this, so please take some time and memorize this. It's coming up on the next slide. So here are your solubility guidelines. This is probably a very handy chart. You can keep this. I have also given you a chart in your chapter summaries. Okay, so you can use that one also, whichever one you find convenient. In any case, you have to memorize these rules. Let me go over them with you. So for the water soluble compounds, alkali metal ions, okay, which is group 1. Now remember, when we say that these are the ions, it means that these are just the cations. They can be bonded with any anion possible, okay? Whether it's hydroxide or nitrate or chloride, whatever it is, it doesn't matter. But remember, just ions do not exist by themselves. They exist with anions, or the cations exist with anions. They have to have opposites in there, okay? And so we're just saying that all the alkali metal cations, whatever salts they form, all of them are soluble, okay? And then also the ammonium ions, okay? All the salts of group 1 cations and ammonium ions are all soluble, no exceptions, okay? That's why this little cell here is empty, okay? Because there are no exceptions to this. Then regarding the anions, the nitrate, acetate, and chlorate ions. Okay, again, remember these are anions, so they can be bonded to any cation, and all of those will be completely soluble. Again, no exceptions. That's the easy ones. Okay, these are the easy ones because they have no exceptions whatsoever. And then we have a whole bunch of halides. Halides meaning coming from halogens. Halogens are group number 7. So halides, chloride, bromide, iodide. Okay. These compounds mostly are soluble, but they have some exceptions. And the exceptions are silver, mercury, and lead. Okay. So which means that if you have silver chloride, mercury iodide, lead, bromide, those compounds are insoluble. But the rest of them are all soluble, which means that you can have iron chloride, iron 2 chloride, cobalt 2 chloride, you can have calcium iodide. Any of those things are soluble. The only ones that are insoluble are these three, okay? Silver, mercury, and lead. Compounds that have sulfate ion, most of them are going to be soluble, except again we have the silver, mercury, and lead, but now we also have some group 2 over here. Group 2 is the alkaline earth, so calcium, strontium, and barium. Okay, and so these are the group 2 cations, so which means that these sulfates are insoluble in water. Okay, all the other sulfates are soluble. So potassium sulfate, iron 2 sulfate, aluminum sulfate, those are all soluble. These ones are insoluble. And then we have the insoluble compounds. Now these ones were all soluble with the insoluble exceptions. Now we have the insoluble compounds with the soluble exceptions, okay, which means that these compounds are in generally insoluble. So for example, carbonate ions, okay, so if you have any compound that contains a carbonate ion, that is going to be generally insoluble, okay, except the ones that have no exceptions here on the top, okay, which is group number 1 and ammonium ion. Now look at all of these, okay, these are all anions, these are negatively charged, so which means that if you have calcium carbonate, that is insoluble, okay, if you have potassium chromate, that is going to be soluble because potassium is right here, okay, and potassium is always soluble no matter what, okay. However, if you have iron 2 chromate, that may not be soluble, okay, because iron does not belong to the exceptions over here. Similarly here also sulfides, phosphates, these are insoluble compounds in general. And then we have the hydroxide, okay, hydroxides also are usually going to be insoluble except again for the group 1, all right, and then there's barium also, okay, so barium is a little bit of an exception that you have to remember here. Ammonium hydroxide is also soluble, by the way. Okay, ammonium is not listed here, but ammonium hydroxide is soluble. So in any case, this is your solubility guideline. Some of it is actually quite easy because if you see the silver, mercury, and lead is pretty much common for everything as far as insolubility is concerned for cations. And then for the anions, it's carbonate, phosphate, sulfide, and hydroxide. I usually don't give you chromates to worry about so much. because you don't encounter so many chromates, but carbonates, phosphates, sulfides, and hydroxide, yes, I will give you those, okay? And so you have to remember these 4, and then you have to remember these 3, okay? And then, of course, group 2 ions. So hopefully you'll come up with some ways to remember this, okay? Because you have to. Let's look at an example, okay, of how this thing works, okay? The question can be phrased in different ways, all right? So first of all, I can give you a reaction, okay, that here is a reaction that's taking place. So predict if there is going to be a precipitate or not. So again, remember this, we talked about that this is a double displacement reaction. So which means that when you have lead in presence of sodium iodide, lead will combine with the negative of the sodium iodide, so iodide, and so you form lead 2 iodide here. The sodium will take the nitrate, and so it becomes sodium nitrate, okay, double displacement going on. Then you look at your solubility rules and you know that you have sodium. If you have sodium, it's always going to be soluble, so which means that this is soluble. Iodides, on the other hand, they have exceptions, and lead iodide is one of those exceptions. So lead iodide is going to be the precipitate here. The other kind of question that you get is, well, here are some compounds, predict if they're going to be soluble or not soluble in water. So you have to just go by the solubility rules. Barium nitrate, for example, is soluble. Why? Because nitrates are all soluble. Silver iodide, not soluble, because iodides are soluble, but not with silver. Hydroxides are insoluble, okay, in general. So these are the 2 typical kind of questions that you will get for precipitation reactions. And then, of course, there is more. The more is writing equations, okay, in aqueous solutions. So when you write an equation, aqueous solution, you really have to expand a whole lot. Okay, so let's go through this. It's a very busy slide, but I'm going to take you through this step by step so you understand what's going on over here. Okay, first of all, you remember these different states that we talked about, because now you have to use them. If you don't use them, your equation might as well be useless, okay, completely. So you should learn how to use the solid, liquid, gas, and aqueous symbols, okay, and use them appropriately. So let's take an example, okay. Our example here is of silver nitrate reacting with sodium chloride, doing a double displacement reaction to give sodium nitrate and silver chloride, okay. So in this case, the reaction is all given to us. We also know what the states are. Otherwise, you should be able to predict that silver chloride is going to be a solid and sodium nitrate is going to be aqueous. I always suggest to you in class also that you call these compounds by names as much as you can instead of formulas. So don't say AgNO3, try to say it by name, silver nitrate. That way you get to learn nomenclature as well as you're saying it properly. Okay, so you don't call it by symbols, you call it by name. Okay, so this is what we call a molecular equation, because in this case, even though these are written as aqueous, we really have not shown any ions in here. So this is called the molecular equation. This is the first equation we write out. The next equation is called an ionic equation, and in an ionic equation, you will dissociate everything that is possible to dissociate. Okay, so for example, silver nitrate is aqueous, which means it is dissolved in water, which means you have silver ions and nitrate ions, and you have one of each. Sodium chloride is also dissolved in water, so it's dissociated, sodium ion and chloride ion, okay, and again one of each. In the product side, now AgCl, okay, silver chloride is a solid. If it's a solid, it's not dissociated, so you leave it as it is. Sodium nitrate, on the other hand, is aqueous, which means that it is dissociated into ions. So you have sodium ions and nitrate ions, and you write that out. This is called the ionic equation. Ionic equations are a little bit long because you're writing all the ions and then you're writing all the AQ, but you have to do this, okay? And that is an ionic equation. And then we have what is called the net ionic equation. We're getting to the bottom part of this now. In the net ionic equation, what you do is you cross out the spectator ions. The spectator ions are what you have on both sides of the equation. Both sides meaning the starting material, the reactant side, and the product side. So if you have any common ions on both sides, you remove them. So for example, in this case, nitrate ion is on both sides and sodium ion is on both sides. Okay, so you cross those out and then you write whatever is remaining. Whatever is remaining is silver ions, the chloride ions over here, and then the silver chloride as the precipitate. Okay, and so this is called the net ionic equation, and this essentially is what is going on in the aqueous solution. The sodium and the nitrate ions, those are not really doing anything. They're a spectator. They're just watching the sport. Okay, and so those are just the spectator ions. Okay, and this is how we write these three different kinds of equations. Let's practice. So here is a solved problem for potassium bromide and magnesium sulfate. So the question is, decide whether the following reaction will occur or not, and if it does, then write the molecular ionic and net ionic equation. Okay, so first of all, our task is to write the products for this one. Okay, and so you figure out the products by the double displacement method. So potassium will react with sulfate. Now you have to know the ions, okay, which means that potassium ion is +1, the sulfate ion is -2. So which means that the product that you will form, which is potassium sulfate, is actually K2SO4, all right? And not just KSO4 as potassium sulfate. So make sure your formula is correct. And then magnesium will react with the bromine on this side. So magnesium ion reacting with the bromide ion to give magnesium bromide, which is MgBr2. Again, the crisscross method of forming a compound. And again, you have to have the right formula over here. And if you're thinking, where am I getting the 2's from? Then remember, you still have to balance the equation, okay? However, our task is not done yet. This is going to be our product that is formed, potassium sulfate and magnesium bromide. So if these are our products, now we have to figure out whether these are soluble or not. And so potassium sulfate is soluble because all potassium ions are soluble, and then magnesium bromide is also soluble, okay, which means that these both are soluble, which means you have no precipitate happening. So there's no reaction going on. Well, what a okay, but anyhow, this is what happens. So in this case, you can add the two solutions without any reaction happening. Well, that was an easy problem, or maybe not so easy, but in any case, let's go on. So in this case, we are writing for sodium hydroxide and magnesium chloride. So yet again, you figure out what the products are going to be by doing the double displacement. Okay, and so sodium will react with the chlorine to give sodium chloride. Now, you have two of the chlorine, but remember, this is going to be dissociated, okay? And once it's dissociated, then it will not be Cl2 anymore, it will be Cl minus, okay? And that's what we'll write out later on, all right? So it's Cl minus, actually you have two chloride ions. So sodium needs only one to make sodium chloride. The other one is still there, and you account for it by balancing the equation, okay? Which we will do later on also. So then you have magnesium combining with the hydroxide to give magnesium hydroxide. So in this case, then you figure out if they're soluble or not, if your products are soluble or not, and sodium chloride is soluble, whereas magnesium hydroxide is insoluble, okay? So then you write the molecular equation. The molecular equation for this is now sodium hydroxide, which is aqueous, magnesium chloride, also aqueous, both are soluble in water, and then you form sodium chloride, which is also aqueous because this is soluble in water, but magnesium hydroxide is the solid, okay? That is the one that is insoluble in water. This is where you would also balance the equation, okay? Because you have to account for the fact that magnesium needs 2 hydroxide, so you need to put 2 in front of NaOH, okay? And then of course you had 2 chlorines that you started with over here with magnesium chloride, so you need to put 2 in front of sodium chloride, and now your equation is balanced, okay? So the molecular equation is where you balance the equation out. Then you write your ionic equation. In the ionic equation, you separate everything out. So which means you have 2 of sodium, 2 of hydroxide, 1 of magnesium, 2 of chloride. Do not write it that Cl2, please write as 2Cl minus, okay, because these are chloride ions, not Cl2 gas, okay, because if you write Cl2, that would be gas. So 2Cl minus, and then on the product side, you still have the 2Na, the sodium ions, and the 2 chloride coming from here, okay, so you have 2 chloride ions, and then of course the magnesium hydroxide, which was a solid. So that is your ionic equation, all completely written out. You cross out your spectator ions, which is sodium, and then you have the chloride ions, okay, that are crossed out. These are the spectator ions, and then you write out your net ionic equation, which is then 2 hydroxide, 1 magnesium ion to give magnesium hydroxide. That's the net ionic equation. See, it's balanced also because you balance the equation right here in the molecular equation. Let's do another. And this one is with potassium phosphate and calcium chloride. So first take the cation of one and the anion of another and make your product. Don't look at it from here, otherwise you will try to form a compound that is insensible, okay? And so don't look at it from here, just take the cation and just take the anion, form your own compound, and then we'll balance the equation later, okay? Similarly, take the calcium, take the phosphate, make your compound first, and then we will deal with balancing the equation, okay? So here you form potassium chloride and then calcium phosphate. Then you figure out the solubilities of both of them, and it turns out that, of course, potassium chloride is soluble and then calcium phosphate is not soluble. So which means that we do have to write the equations out. So the molecular equation then is the potassium phosphate, calcium chloride, plus potassium chloride and calcium phosphate. This is the place where you will balance the equation. Please make sure your formulas are correct, which you should write, okay, from here. So once your formulas are correct, then go ahead and balance the equation out, okay, using the stoichiometric values, okay, over here, the coefficients. Once it's balanced out, go ahead and write the ionic equation. So now again, let's talk about this, okay, because you have 2 of potassium phosphate. So you have 3 potassium ions. Do not write it as K3 because there's nothing like K3, okay? So there are 3 potassium ions multiplied by 2. So there are 6 potassium ions. There are 2 phosphate ions, 3 calcium ions, and 2 times 3, 6 chloride ions. Not 3Cl2, but 2 times 3. Okay, because these are chloride, these are separate ions, okay, that exist by themselves. You just happen to have 2 of them over here, okay, in the formula. So separate them out, please. So 3 times 2, 6 chloride ions, and in the product side, 6 potassium ions, 6 chloride ions, 3 calcium, but this is our solid. So oopsie, that is the solid, okay, no ionization over here. Then you go ahead and cross out your spectator ions, which is potassium, and chloride, okay, all crossed out. Your net ionic equation is 2 phosphate ions plus 3 calcium ions to give calcium phosphate, all nice and beautifully balanced out, okay? Don't forget the AQs and the solid, okay? That is what makes it an ionic equation and a net ionic equation. You have to do that in the molecular equation also, okay? For this chapter, you just have to do it.
So let's look at another example here, and this is for silver nitrate and sodium sulfate. So aqueous solutions of silver nitrate and sodium sulfate are mixed. Write the net ionic reaction for this. So luckily for us, the equation is given for you. Usually in class practice and all that, I don't give the equation, so you have to write it yourself. So silver nitrate is AgNO3, sodium sulfate is Na2SO4, and these are the products. And how do we know this? Because this is precipitation. So you do a double displacement reaction. So silver will combine with sulfate and sodium will combine with nitrate. Now make sure you write all the products in their proper formula. So NaNO3, not Na2NO3. Okay, that would be wrong. Just because it's Na2 over here doesn't mean that you'll have 2 sodium here also. The NO3 is -1, Na is +1, so 1-to-1 ratio there. So once you have this equation, then you can go ahead and balance it out. And so because you have 2Na over here, okay, sodium 2, this becomes 2NaNO3 and so on and so forth. You know how to balance an equation. So then we have to figure out what the solubility of the salts are. We know the left side is all aqueous, okay, because it tells us in the problem. So we know the left side, the reactants are all aqueous. So we have to figure out what happens on the right hand side. So in the right hand side in the product, we know that nitrates are all soluble, or you can also think of it as sodium. Group 1 salts are all soluble. So this means this is going to be soluble, which means it's aqueous, and then sulfates are actually insoluble unless they are combined with group 1, which it is not. So here this is going to be insoluble. So then our molecular equation becomes the silver nitrate, sodium sulfate, and then sodium nitrate. Now we can go ahead and remove that question mark and put aqueous here because this is soluble. And then the silver sulfate is not soluble, so that is a solid. Now remember, we have to write the net ionic equation. We've just done the first part, which is writing the molecular equation. Now we go on to the ionic equation. So in ionic, you'll go ahead and take all the aqueous soluble, all the water soluble salts, and you will dissociate them. So as we have been doing before, this is 2AgNO3, so which means you have 2 of AgNO3, so 2 of silver, 2 of the nitrate also. Okay, so make sure you use the proper coefficients as you're going along. Do not separate out the nitrogen and oxygen for the nitrate. Okay, leave it as it is because it's a polyatomic ion. Na2SO4, now you have 2 sodium here, so that 2 becomes the coefficient. And then you have only 1 sulfate, so that's this over here. Everything on the reactant side is aqueous. On the right hand side, you have the 2 sodium nitrate, so 2 sodium, 2 nitrate, both aqueous because this is soluble, and then this one is not soluble. So silver sulfate remains the same, and that is a solid. Okay, so this is then our ionic equation. And then what we have to do is cancel out what we call the spectator ions, okay, and then that will give us our net ionic equation. So we have a few spectator ions here, well, 2 actually. So we have the sodium on the left side and sodium on the right hand side. We also have the nitrate on the left side and nitrate on the right hand side. So that gives us our spectator ions that are gone, and then we are left with the net ionic equation, which if you pick that out, it is going to be 2 silver, 1 sulfate to give you the silver sulfate. Now if everything is fine and you balance the equation properly, you shouldn't have to balance it again. So this is how you would figure out for a precipitation equation, or just simply writing a net ionic equation. Here are your keywords and concepts for this PowerPoint. You should be able to classify something as electrolyte or non-electrolytes and things like that. Recognize the acids because acids are covalent, however, they are electrolytes, all right? Then there are the different types of reactions that we have, which is synthesis, double displacement, and so on. You'll be able to classify reactions in one of these. And then, of course, we covered precipitation reactions. We covered a lot of reactions, so I showed you all the different types and different types of questions that you can get. So make sure you know your solubility rules and learn how to write those net ionic equations.